Okay, first of all, I'd like to apologize for not being there in person. As it turns out, the burden of the snow was a little too much for me to bear, so you're left with me on YouTube. It is what it is. Our lab will continue next week. Okay, we've been working with stoichiometry, and stoichiometry is a system of taking a real world value from some part of a reaction and take it to any quality to any other part of the reaction. Okay, and if we were outside of chemistry, we could say something like, I guess we could build bikes. 2 tires plus 1 frame equals or yields 1 bike. Okay, and if I gave you any real world value on either tires, frames, or bikes, you could calculate the other two. Okay, you could go from reactant to reactant, product to product, product to reactant. Okay, any which way you can think of. And when we're doing those problems, I only gave you a specific value for one aspect of the reaction. Okay, I gave you some numbers on either a single product or a single reactant and asked you a question. But now we're actually going to start talking about what to do, how to handle a situation. Okay, if we have actual real world numbers for perhaps both reactants. Okay, and I use this building bikes just to kind of illustrate the point here that, you know, how many bikes could you make from, let's say, 73 frames? And our mole-to-mole ratio is obviously 1 to 1. And of course, that's 73 bikes. That's easy to see. Okay, well, what if I said, how many bikes could you make from 73 frames and 200 tires? Okay, so I'm going to take the tires over as well. Mole-to-mole ratio now is 2 tires to 1 bike. Okay, and this is obviously 100. Well, now I'm going to ask you, put it all together in one sentence. How many bikes could you create from 73 frames and 200 tires? Okay, you got a 50-50 shot here. You got 73 or 100. But taking both into account, okay, it should be quite obvious that you can only build 73 bikes. Okay, you can only build 73 bikes because you run out of frames. Okay, the frames are, okay, we're going to label this as the limiting reactant. Okay, the limiting reactant because it limits the reaction. Okay, limits the reaction meaning, okay, i.e. runs out first. I don't have enough frames. I run out of frames. Okay, I still have tires left, so what we call the tires would be an excess reactant. Okay, limiting reactant would be, again, what runs out faster. Okay, excess reactant means you're going to be left with extra of that reactant, extra tires in this case. Okay, we can't make 100 bikes because our frames, unfortunately, can only make, 73. We only have 73 frames, so that's what's holding back, that's what's limiting the reaction. Okay, so what would actually be made would be the lesser of the two amounts. Okay, this type of stoichiometry is called limiting reactant, limiting and excess reactant. And even though we're dealing with bikes here, okay, it's basically the same exact thing when we do chemicals. Okay, so if we pull that up, let's get our problem. Okay, it looks like this. And you have this one as well. What am I doing here? It looks like I'm making table salt. It's a balanced equation with the two NAs and the two NaCl's. Okay, and I'm giving you 40 grams of sodium, 85 grams of Cl2, of chlorine. So I have 40 and 85. Okay, and I'm asking how many grams of NaCl can be produced, okay, with those two amounts. And the same as before. Well, first of all, let's just take a step back and notice that I have to take both values into account, both the 40 and the 85. And on the face of it, I can't make any decisions based on the grams. I can't say that sodium must be limiting because it's less. It's 40 compared to 85. Can't do that. What I have to do is I actually have to take a step back here and do the hard work of taking my 40 grams of sodium, okay, via stoichiometry all the way to grams of NaCl. Okay, first move would be from grams to moles. I'm not going to do all the work here, it's on your paper. Mole to mole ratio to switch chemicals, okay, and then moles to grams. Next, I'm going to, when we actually do that number, we're going to get 101.7. I'm going to do the same thing now, and I'm going to start with my 85 grams of Cl2. And I'm going to do the stoichiometry once again. It's going to be the same steps, ... Okay, grams of Cl2 over moles of Cl2. And I'm going to do the hard work here with my calculator. I'm going to find out that this is 140.1 grams. Okay, so to answer the question for A, how many grams of NaCl can be produced, it's going to be the lesser amount. Okay, I had both reactants. I took them both to the same product, and I'm actually choosing the lesser amount. Okay, what does that mean? It means that Na sodium is the limiting reactant. We call it the LR. It means that chlorine is the excess reactant. Okay, limiting reactant, excess reactant, and this is what the 101.7 would be the actual product, or in theory, that's what you should produce. What does the 140 mean? It's a theoretical number that if you had unlimited sodium, you'd create 140. We don't have unlimited sodium, so the number's basically useless. Okay, you actually have to go through the whole mole to mole ratio in order to come up with these numbers. There's a few ways to actually do these calculations. They all involve the same amount of work. This is just as easy as any other, is to do both stoichiometries, take them both to product, take the lesser amount. Okay, so the answer to A is 101.7. What is the limiting reactant? The answer to B is sodium. Okay, now the answer to C is something we have to actually think about for a second. How many grams of excess reactant will be left over? Okay, how much will you have left of the excess? Okay, I want you to actually take a step back here and think about this. If we created 101.7 grams of sodium, and we started with 85 grams, 101.7 grams of NaCl, and we started with 85 grams of Cl2. Is there a simplistic way we can actually figure out how much Cl2 we actually used? Okay. I want to know if I make 101.7 grams of NaCl, is there a method for me to find out how many grams of Cl2 I will need to actually react? Okay, how much of the Cl2 I actually used? And of course, we can just do that with stoichiometry. Okay, again, grams over mole. I'm sorry, moles over grams, mole to mole. Last step, moles in grams of Cl2. Okay, so look what I'm actually doing here. I'm starting with the actual product of what was produced. This was my answer for A, 101.7. And I'm using stoichiometry. Okay, I'm not filling in the parts. It's all in your worksheet. I'm using stoichiometry to go to grams of Cl2. Okay, this is going to indicate grams of Cl2 used. Tablet's giving me some issues right now. Okay, and I believe that answer is 61.7. Okay, so we used up 61.7 grams of Cl2. We started with 85 grams of Cl2. So how much of the excess is left over? Well, it's going to be 85 grams of Cl2 minus 61.7 grams of Cl2, yielding or equaling 23.3 grams of Cl2. Okay, that's my answer for C. Okay. I have my original Cl2 value, and I'm subtracting the Cl2 that I actually used. Okay, 61.7 grams of Cl2 will be used with my 40 grams of sodium, and it's the excess reactant I will have leftover Cl2. How much? 23.3 grams. Okay. Not so bad. It's just, I'm taking one problem and we have to do many stoichiometries. But each stoichiometry on its face is not any more difficult or easy as before. It's the same. Okay, it's just that it takes a few extra steps. Lastly, okay, we're going to talk about percent yield. Okay, we've used percent error before. This is percent yield. And it's a measure of efficiency. Okay. In real life, when you're doing some sort of reaction in a lab, it's never going to be a perfect world. The conditions are always going to, something will be going askew. Some reactions just don't react cleanly or efficiently on their face, okay, all the way to the root chemistry. That you're not going to produce as much as you actually calculated that you would produce. Okay, percent yield is a matter of a measure of efficiency for a reaction. And we have a pretty easy calculation here to go along with it. It's, okay, your actual lab result on the top. Okay, so it's the lab result. That's your real world number. And on the bottom would be your math result or your theory result. Okay, theory is pencil and paper, right? You're just using stoichiometry and calculations. Lab is you're actually getting your hands wet and actually doing the work in the laboratory. So the theory result is the denominator. It's always the absolute highest mark you can achieve. The lab result is typically not as large as the theory result, so it goes on top as the numerator, and because it's a percent, we multiply it by 100. Okay, so these are very simplistic calculations for percent yield. I'm actually asking you one in D. If you made 87.48 grams of NaCl in a lab, what is your percent yield? Okay, this is all on the inputs of the 40 and the 85. Okay, so if I only made 87.48 grams of NaCl, have to get a new stylus here. What is my percent yield? Well, I made 87.48 in the lab, and via stoichiometry, I should have been able to create 101.7. Okay, so I would just run these numbers through my calculator and find out that my actual efficiency for this lab is roughly 86%. Okay, 86. We'll just call it 86%, 0.02. Okay, so maybe I spilled something. Maybe it's a humidity thing. Maybe I had the temperature wrong or the pressure wrong. I don't know. All I know is that I did not create as much product as I hoped for or what I calculated for. I have an 86% rating, which in a lot of ways is actually quite high. Okay, some reactions you can run and have a percent yield of 99.99%. Okay, some reactions you run and you're lucky to get above 50 or 60%. Okay, so it's just the nature of the beast. Our percent yield calculations are usually pretty decent. Okay, sometimes they involve just a little bit of algebra, moving things around, but nothing we can't handle. So hopefully we have enough now that we can actually finish up those problems independently, and we'll deal with this again next week.